Cool. Yeah, thanks for having me. I'm Richie. I'm the co-founder and CEO of WarpStream, and yeah, I'm going to talk about how we kind of rebuilt Kafka from the ground up with no disks. So if you're not familiar, WarpStream is a drop-in replacement for Apache Kafka. It implements the Apache Kafka wire protocol. Uses standard Apache Kafka client, but the implementation is completely different. Before I get into the details of how WarpStreams works, I want to explain a little bit about tiered storage, because that's a question I always get asked about is like, what's the difference between WarpStream and what's the difference between tiered storage? So if you're not familiar, tiered storage is a feature in Kafka and many other systems that allows you to take data that's been stored durably on disk, copy it to S3, and then delete it from the local disks. The reason people like to do that is cloud disks are really expensive. So if you're retaining data for a long time, like if your Kafka retention is 3 days or 7 days or whatever it is, 80% of your total cost for a cluster can just be paying for EBS volumes or SSDs. And so, if you kind of do the math for software running in the cloud, an EBS volume, GP2, is about 10 cents per gigabyte pre-replication. Once you replicate it 3 times, it's about 30 cents per gigabyte. Probably don't run your Kafka cluster at like 100% disk utilization. So once you leave some headroom, you're probably at like 50 to 60 cents per gigabyte. Whereas with S3, you can store that data for 2 cents per gigabyte per month, right? You can kind of play with these numbers a little bit. You can do double replication versus triple replication. You can do, local SSDs instead of EBS. That's a little bit cheaper too. But kind of fundamentally, if you want to retain a lot of data for a long time, you kind of have to put it in S3, or it's going to be a lot more expensive than it needs to be. So that's why people, like tiered storage. This is not, there we go. So tiered storage is good. It helps, but it's not really enough, I think, to really make what people want to do with Kafka in the cloud possible. And so with WarpStream, what we set out to do was get rid of the disks in the brokers entirely. And the reason we want to get rid of the disks is that most of the problems that people have with Kafka from an operational perspective and a cost perspective are a result of the fact that the brokers themselves are stateful. So if you've ever been on call for Kafka, you tried to scale it in, you tried to scale it out, you have to deal with things like node replacements, partition rebalancing, disk getting full, disk imbalances, failing disks, topic partition leaders, all that kind of stuff, right? And just in general, balancing is always a problem. All of those problems essentially arise from the fact that specific topic partitions are owned by specific brokers, and those brokers are storing copies of data that can't be lost. The other reason we kind of set out to build something that didn't have any disks at all was to address kind of the networking problem that happens in cloud environments. So even if you're running Kafka, if you're running it at high scale, but you're not storing the data for a long time, let's say you only keep the data for 8 hours or 12 hours because you're processing it with, Rising Wave or something, or you're dumping it into your data warehouse or whatever it is. At high volumes, 80% of the cost of a kind of a typical Kafka cluster running in 3 availability zones will just be networking fees. The reason for that is because the brokers are stateful. When your producer needs to write data for a topic partition, it has to write data to the topic partition leader. The topic partition leader is not necessarily going to be in the same zone as the producer. In fact, 2/3 of the time, it won't be. And so every time you copy data between availability zones in basically all 3 of the major clouds, you have to pay 2 cents per gigabyte. So 2/3 of the time, the producer and the topic partition leader are in different zones. And then once you get the data to that topic partition leader, it then has to be copied 2 more times to followers in 2 other availability zones. And if you do the math on that, it ends up being 5.3 cents per gigabyte written through Kafka, which when you think about it, you can store data in S3, a gigabyte of data in S3 for 2 months for the same amount of data, for the same cost as just copying it over the network one time. So this is a big problem, basically, for high-scale Kafka clusters in cloud environments. And that was another problem that we wanted to solve. And doing that means you have to get rid of the disk on the brokers. Otherwise, you won't be able to solve the replication problem. So basically, our kind of our thoughts with WarpStream was that 0 disk would be better. If we could do everything with 0 disks, that would be better. And so that's what we built. This is kind of like a very high-level overview of WarpStream. I'm going to go into like more technical details over the course of the talk. But at a very, very high level, instead of Kafka brokers, we have these things called agents. And the thing that's cool about agents is that they're completely stateless. So they have no EBS volumes, they have no SSDs, they have no disks at all. And no agent is special. So there's no agent that's like the leader for an individual topic partition. Any agent can handle writes for any topic partition, and it can also handle reads for any topic partition. And so since no agent is special, what that means is that your producer can always talk to an agent that's running in the same availability zone as it, and so can your consumer. The consumer reading from the same availability zone is possible with Kafka as well. There's a feature called fetch from follower, but the producer part is not, right? You can't zonally align your producers in Kafka, but with WarpStream you can. The other reason that's really important is that we never have to copy data between the agents running in different availability zones. Instead, what happens is when your producer writes data to an agent running in the same zone as it, that agent buffers the data for 250 milliseconds by default. You can tune it. Once it's buffered that data for 200 milliseconds, it flushes a file to the object store, commits the fact that that file was flushed to the metadata store, and then acknowledges the request back to the producer. And what that means is that essentially what we end up doing is using the object storage in S3 layer as both the storage layer and the network layer. So when this consumer wants to read data that was written by this agent, it does so by reading it through the object storage layer. And when you do that, you don't pay any of those expensive networking fees because networking between VMs and object storage is always free in all major cloud providers. So we treat the object storage layer as both the storage layer and the networking layer. That gets rid of all the networking fees, and it also gets rid of all the EBS volume fees. So this ends up being basically a lot cheaper than running Kafka at scale. But the trade-off you make is that it's a higher latency system, and I'll talk about that too. The other thing to keep in mind is that you get the same durability guarantees as you do with Kafka running in ax equals all. And the reason for that is the agents will never acknowledge a produce request until the produce request has until all the data has been durably persistent in S3. So it's the same durability guarantees as Kafka, just higher latency. And the reason we're able to do this, actually, sorry, before I get into how we're able to do it, I want to talk one more thing about cloud unit economics, and then I'll get into the guts. But when you're building a system on top of object storage, there's basically like two numbers you need to know. One is how much you pay for a put request, and the other is how much you pay for get requests. Those are like the only two numbers that matter, basically. And so the thing to know is, that those look like really low numbers, but at scale, if you do hundreds and thousands of these per second, they add up. And get requests are 10 times cheaper than put requests, but still at scale, they will add up. The other thing to know about object storage is that storage is really, really cheap, right? I've been talking about that the whole time, basically. And networking between VMs and object storage, regardless of availability zone, is always free. And so this has some really important implications for how we design the storage engine. It means that we have to minimize, everything we have to do has to minimize the number of put requests and the number of get requests that we do. But it's okay to increase the amount of data that we store or to do additional networking because those things are either cheap or free. So anytime we can trade space amplification for reduced put and get requests, or do more networking to get less put and get requests, that's usually a good trade-off. And so you'll see how that falls out of the design. So the first thing we do, if you're familiar with how files are stored in Kafka, so if you have a broker in Kafka and it's the leader for a bunch of different topic partitions, it'll have mutable segments for each of those topic partitions on disk, and then the writes just go to the end of those. That works fine when you're writing data to EBS volumes or SSDs, but if you did that with the object storage layer directly, you'd be making tons of put requests, and the system wouldn't be cost effective, especially when you have a lot of topic partitions, right? And so the big thing with like WarpStream storage engine, the thing that we're always trying to do is decouple the number of topic partitions in your cluster from the number of S3 API operations that we perform. And so the way that we do that is that instead of making segment files per topic partition, the agents make one segment file every 250 millisecond, and that segment file contains batches of data from every topic partition that the agent received data for in that 250 millisecond window. So no matter how many topic partitions you have in the cluster and you're writing to, you're going to make exactly one S3 put request every 250 milliseconds per agent. So it's, if you have 4,000 partitions or 10 partitions, the number of put requests is the same. Because we made this design decision, there's now like a lot of other problems that we have to solve. And so the rest of the talk is me basically explaining how we solve kind of all those problems one by one. So the first problem that kind of comes up when you eliminate the topic partition files is exactly how does the write path work, right? So this is, you can imagine you have a Kafka client, it's buffering and compressing data. It sends a produce request to the agent. The agent also buffers the data, flushes the file to the object store, commits it to the metadata store. And then finally, when all of that is done, the produce request is act back to the client. So that part's really straightforward. The problem is this only works kind of naively if you only have one agent, right? If you have two or more agents and both of those are writing data for the same partition at the same time, you kind of have a problem, right? Because data in Kafka is ordered within a topic partition. And so at some point in the system, we need to decide which data comes first. And so the way we do that is we have this, when we commit, so when we flush the files to the object store, we actually don't know which batches come first yet. We haven't assigned offsets. So we can flush data to the object store with kind of massive concurrency. And only when we commit the data to the metadata store do we actually logically serialize the commits and determine which offsets come first. And so you can think of it as like the data plane runs kind of with massive amounts of concurrency and parallelism, but the control plane runs kind of in a logically serialized way. And so another way to think about this is that the metadata store basically acts like a Raft consensus group, but it acts as a group leader for essentially the entire cluster instead of just a single topic partition. And the reason that we can scale essentially a single consensus entity to the entire cluster is because the consensus only has to process the metadata. It doesn't have to process any of the raw data. And so the amount of, if you're writing gigabytes per second of data through this cluster, the amount of metadata that has to be processed is only like hundreds of kilobytes per second. And so that's how we handle the fact that basically we have no topic partition leaders. So once we solved that problem, the other problem we had to solve was that, when you go to read data in Kafka, you go to either the topic partition leader or one of the followers. Those brokers will have all the data that you need for that topic partition kind of laid out contiguously on disk, and it's really easy to access and read. With WarpStream, the data for that topic partition may be spread over many different files, and it's going to be kind of commingled with a bunch of other data, right? And so the control plane metadata store thing I was talking about in the other slide kind of knows in each file where each topic partition starts. So we know where we want to start to look. But we still have to handle the fact that, if you did this naively, if every consumer came in and just issued GET requests directly for the data and object storage, if you have hundreds or thousands of consumers and they're all reading for hundreds or thousands of partitions, the number of GET requests you would do would be essentially, n squared with, not m squared, it'd be m by n, where m is the number of partitions and n is the number of consumers. It'd be a really, really, really big number and it would be too expensive. So what we do instead is, in this diagram, I have 3 consumers for my WarpStream cluster. The blue consumer represents one consumer reading from partition 19, the orange one's reading from partition 2, and the green one's reading from partition 3. All of these consumers have in-flight fetch requests. They're all reading different partitions and different segments of data. And what we do in the agents is we build essentially this distributed file cache. So it's a read-through cache. It's, if you delete the cache, nothing bad happens. You don't lose any data. But we build a hash ring, and basically every 16 megabytes of data in a given file gets assigned to one agent. And anytime we need to read any data in that kind of 16 megabyte chunk, the read for that gets routed through a specific agent who's the owner for that segment. So in this case, all 3 consumers are reading some data from a partition. They're getting routed to the same 16 megabyte chunk. And then that chunk is owned by agent 2. And agent 2 has an in-memory cache. It'll detect that these 3 requests are all concurrent. It'll deduplicate them, turn them into one 4 megabyte read that goes and reads 4 megabytes of data at once from the object store, loads all of that data into memory, chunks it up into really small pieces, and then loads that all into the cache. Once it's loaded all those little chunks into its in-memory cache, it'll then serve all the different consumers directly out of memory. It's kind of hard to visualize what this would look like for a live workload where you have hundreds or thousands of consumers and hundreds or thousands of partitions and everything's happening at the same time. But the way it boils out is basically for every 4 megabytes of data that you write, you will issue exactly one GET request. We issue exactly one GET request for every 4 megabytes of data that needs to be read in each availability zone. So the number of GET requests, if you have one consumer or 10, and if you go from like 10 partitions to 10,000 partitions, the number of GET requests stays the same as well. So we've effectively decoupled the number of GET requests, not only from the number of partitions, but also from the number of consumers. And it's really purely a function of the number of availability zones and how much data you're writing. And if you can, if you do the math on how much object storage API calls cost, if you can do reads in 4 megabyte chunks and use all of that data, it's super, super cost effective. It's kind of hard to explain this like with my hands. We have a blog post that goes into more detail on this on our website, if you want to check it out. Cool. So that's the live edge, right? So that's how we handle all of the reads for the kind of live consumers that are tailing the cluster. But that's not how people always consume from Kafka, right? Sometimes you read older data. And so you can imagine that this entire diagram here, I've compressed it over here into this thing over here. And so for the live edge, you have this smart distributed cache. You get to share all the I/O. Everything's good and happy. But eventually one of your consumers will lag or it'll want to go and read a bunch of historical data. And then you have a problem, right? Because this consumer over here has no opportunity to share I/O. And it's basically going to be, since your topic partition data is spread over a bunch of files, this lagging consumer is going to have to go and make one GET request for every file that's ever been written. And if you can imagine that happening repeatedly or once for each topic partition that you have, that's going to become really expensive really quickly. And so the way that we solve that is the same way that you solve this problem in like a traditional data lake or an LSM. We just run compaction, right? Compaction basically takes a bunch of small files that were written for ingestion and turns them into one bigger file. And when we do compaction, that brings data for the same topic partition that's spread really far away in different files, and it brings it closer together. And so when this historical consumer comes in and needs to read, an older topic partition from start to finish, the number of files it's going to have to read is going to be really small because we've compacted all the historical data. In WarpStream 2, we run compaction like really aggressively. This isn't something that happens like hours or days later. The files that are created by the agent for the live workload go through their first round of compaction in like an active cluster within a P99 of like 8 seconds. The second round of compaction usually happens like 2 minutes after that. So the compaction runs extremely aggressively and very quickly. If I explain this is really hard to explain with my hands. And if I do, I don't think I'll have time for questions. So I'm going to skip over this topic real quick and just get to the other stuff. Okay, so just to give you an idea of how expensive interzone networking is, what this graph shows is if you're running a Kafka cluster yourself, you're running it in 3 availability zones and you're writing a gigabyte per second through it. So you have like a big logging workload or something, right? Let's pretend that the hardware for Kafka and WarpStream is the exact same amount because it kind of doesn't matter. The amount of interzone networking you have to do a 1 gigabyte per second workload in Kafka, you're going to end up spending $1.68 million per year just on interzone networking if you run that workload in 3 AZs. With WarpStream, the networking fees go to almost zero. We do add in object storage API fees that weren't there, but you can see it's like not a 1-to-1 ratio. The object storage API fees are basically 1/10 the cost of the interzone networking fees. And this isn't even factoring ABS. So that's why we kind of like focus so hard on making this architecture work, because it kind of almost doesn't matter anything else you do. If you don't solve the networking problem, it's going to remain really, really expensive, at least if you want to run in multiple AZs. Now, the downside is that the minimum cost for a WarpStream cluster is about $600 a month. You basically can't do it cheaper than that because you have to have 3 nodes, each doing 4 put requests per second. But as you scale, it gets kind of more and more cost effective. The other thing I want to talk about latency, I said earlier in the talk that WarpStream is a higher latency system than Kafka, which it is. So if you have like a really well-tuned Kafka cluster, you can get your write latencies down to like kind of like double-digit milliseconds. With WarpStream, the kind of P99 producer latency you'll see is going to be between 400 and 500 milliseconds. And the end-to-end latency you'll see between kind of like 1.2 and 1.5 seconds. So higher latency, but still very much kind of like real time and sub-second. The other thing to keep in mind is that, you know, all the major cloud providers are essentially introducing new tiers of object storage. So for example, in AWS, they have this tier called S3 Express One Zone. And what S3 Express One Zone is it's a version of S3 that's only available, like the bucket only lives in one zone, but it's much lower latency than S3 standard. And so what we do with this with WarpStream is, since we still want to be able to tolerate the loss of a single availability zone, is we make 3 S3 Express one zone buckets. And then the agents write data to a quorum of 3 buckets. So as long as your writes succeed in writing to 2 buckets in 2 zones, we consider the write a success. And by doing that, we can get the P99 write latency down from like 500 milliseconds to 140. And we can get the end-to-end latency down from 1.2 seconds to 400 milliseconds. The other thing that's kind of interesting about S3 Express One Zone is that the storage costs are 8 times higher. So it's really expensive to leave your data in S3 Express. But since the WarpStream agents are doing compaction anyways, what we do is we land the data into S3 Express One Zone, then we immediately compact it into S3 Standard. And so what you get is kind of like a form of tiered storage, but the tiering happens within seconds, and both tiers are essentially kind of quote unquote infinitely scalable object storage. That's it. So that's WarpStream. All right, so I think I have a few minutes for questions. Yeah.
What questions that people have sent it
over Zoom or? Okay, cool.
Yeah, does this work? Okay. First one is, you mentioned that on the producer write path, the agent flushes every 250 milliseconds. So
by default, yeah.
By default. And so what happens if an agent crashes before that is one question.
Yeah, it's the same thing in Kafka, which is that we don't acknowledge the produce request until the write is succeeded. So while the agent's batching the data in memory, from the client's perspective, the request is still in flight. So if the agent crashes, the client will see a timeout and they can retry on another node. Which is the same thing you get with Kafka, right? When you write to Kafka, it's not instantaneous. The broker could crash while the write's in flight. The client will get an error, and then you wait for a topic partition. You wait for a leader change, and then you write to the leader. So it's the exact same as Kafka.
The second question is, how do you typically size agents?
That's a good question. It really depends on the workload. You know, there are some workloads I've seen where like the producer is extremely well behaved and you can write like, you know, 0.5 gigabyte per second on 2 very small agents. But most people's workloads are like way less well behaved than that. I think I usually tell people 10 megabytes per second per core. I think it's 10 megabytes per second compressed per core. The thing that has a really large impact on that too is the number of topic partitions. If you have thousands and thousands of active topic partitions and your producers write kind of randomly to all those topic partitions, it's more expensive. But usually I tell people about 10 megabytes per second per core compressed.
And can agents be configured to run arbitrary roles such as?
Yeah, you can actually. So that's, okay. We have, yeah, exactly that. You can at scale, like I usually for smaller workloads, you just run all the roles in one binary. But if you want, you can create a group of agents that only handle writes. Then you can make a group of agents that only handle reads. And then you can make a group of agents that only run compactions. And you can keep everything isolated, auto-scaled independently, and you can even run them on different instance types too. So you can really micro-optimize it at scale if you want.
And can you basically run custom code on these agents?
Oh, run custom code in the agents. We have a thing in there called, we use Benthos to do that. I don't know if you're familiar with it, but it's kind of like Kafka Connect, but written by one guy in Go. It's actually a really, really good project and library. We embed that directly in the agents, so you can use that to run kind of custom code.
Okay, I have 2 more. I think
Sure.
This is good. This is being recorded, right? Okay, that's great. So The next question is DR for WarpStream as simple as making a snapshot of the S3 bucket?
It depends on what you mean by DR.
Recovery in another
In another region?
region.
In another region. So there's two ways to do it. One is you can just do it the way people do it in Kafka. You can like run Mirror Maker and just copy all the data to another WarpStream cluster. There's a couple other kind of interesting things you can do. It's not quite as simple as just like enabling bucket replication in the cloud provider. But a thing we're working on right now is basically the ability to have like multiple, like synchronously replicated multi-region active WarpStream clusters. So basically a WarpStream cluster that's flexed across 3 nearby regions. And the way that works is we use a multi-region metadata store that's strongly consistent, and then the agents write to a quorum of 2 buckets in multiple regions. Once you start doing stuff like that, it becomes incredibly expensive. Like inter-region networking is crazy expensive. But if you have workloads where you like really need all of your data to be, if US East 1 like gets blown off the face of the earth and you can't lose data, then you can do crazy stuff like that. It's mostly like banks and stuff that are interested in stuff like that.
This last question is a long-winded one. I think this is about your recent blog post as well, which is about reasoning about latency with tiered storage in Kafka. And that segments are having to be actively kind of downloaded and then served up. So in this case as well, I think you mentioned about it that on the read path you have caching. So how easier is it to reason about latency in WarpStream in contrast?
Yeah, the WarpStream and the latency in WarpStream is higher than Kafka not running in tiered storage mode, basically. But it is extremely consistent and predictable. Once you enable tiered storage in Kafka, if you're reading like the data that's still on the disks, obviously it's fast. As soon as you hit any data that's been archived to S3, it becomes extremely slow and extremely unpredictable. So if you are reading data that's been tiered frequently, the performance of WarpStream is like an order of magnitude better and much more predictable.
Final questions actually from me before I open it up to the audience. So I think a lot of Kafka vendors have gone to great lengths to support the Kafka protocol. So I think the question is, have you come across instances where supporting the protocol itself is a limiting factor, or do you see opportunities in making?
Yeah, it's the most annoying. It's so annoying, dude. It's a really bad protocol for cloud native stuff. It just really doesn't really make any sense anymore. The protocol is basically all of the implementation details of Kafka just directly exposed, and Kafka it's like a very low level system, so it's super annoying. The flip side though is that everything speaks Kafka. So like we didn't have to write any client SDKs. I didn't have to write any integrations. Didn't have to write Kafka Connect. I don't have to write Debezium. We implement the protocol and everything just works. But yes, it's super annoying. Like we actually started with the Kinesis protocol because I think it's a better protocol for kind of modern kind of cloud native stuff. It just turns out like no one cares that you support Kinesis. So yeah.
And do you see vendors eventually diverging away and kind of looking at their own differentiated capabilities?
Just 100%. It's already happening. You're already seeing people doing stuff with like Iceberg. That's essentially a new protocol. We're introducing a new protocol soon for interacting with WarpStream, kind of for more like batch and data lake oriented things. So I'd say it's already happening, and I think that's okay. I think Kafka will remain kind of like the lowest common denominator, and people will. It's good. It's good for people to be exploring new protocols and seeing what's possible with different approaches.
Awesome. Superb, Doug. Thank you.
Yeah.
Is there any routing to the agents that happen based on the topics I guess Apache
Yeah, that's a good question. Are you talking about writes or reads? Probably writes. Yeah, we can do that. Like if it's just a setting. Like if you go change, it's like in our documentation. There's like if you add a flag in your Kafka client ID, it behaves like Kafka, where we take all the topic partitions and we assign them to all the agents in a round robin manner. So you can do that. We've just found in practice that you get more predictable performance and less hotspotting with the strategy we take. So for the vast majority of workloads, I think the default strategy we use is better. But for some particularly like pathological workloads, like someone's like, you have one producer writing to 1,000 partition and it just, each record goes to a different partition or, whatever. Enabling that other setting can be beneficial. It kind of depends on whether or not your producer cares whether all that data is committed atomically or not. If your producer doesn't care that all of the writes to all of the partitions succeed all at once, then it's actually more beneficial to do what you're saying. But if you have like 1,000 records and you're writing to them to 1,000 partitions, and you need to wait for all of those things to finish, it's actually much better to write them to a single agent, because then you're only exposed to the latency of one agent instead of all the agents in the cluster. I don't know if that makes sense. Yeah.
What if I want to ensure the order? Let's say I have 1,000 records that I'm trying to insert.
Yeah.
But because it's purely stateless and each request could go to any agent, the ordering that at which
You get
I inserted is not going to be.
it's the exact same ordering semantics as Kafka, actually. Like if you provide a batch of records and they're in this order, when they end up in the topic partition, they'll be in that order. The thing that you just don't know about is if you have two producers on two different machines producing to the same topic partition, you don't know which one of those batches is going to commit first, but it's the same in Kafka, right? Like when you write to Kafka, you have multiple people writing in parallel. Eventually the broker decides which one happened first. Yeah, and in our place, it's the metadata store, serializes everything and decides the order. So everything, you get the exact same ordering semantics as Kafka. There's just a larger window of time where there's like in-flight requests, but it can like, you write to Kafka and then, it gets stuck in a router for 50 milliseconds, or, Netty reorders the threads, and there's a bunch, like all the same stuff is happening all the same time in Kafka. So it's the same thing. There's just a larger window of time where that's happening. But if you write to WarpStream and then you get a success back and then you write again, the second write is guaranteed to have offsets higher than the previous write. So it's externally consistent, if that makes sense.
The metadata store is highly available, I assume?
Yes, it's quadruply replicated.
Right.
Yeah.
If you could share anything more about that, that'd be cool.
That's kind of, we don't talk about that too much. It's like the secret sauce stuff, but it's, yeah, it runs in multi-AZs and it's quadruply replicated. It's extremely custom. It's not like, oh, we use Zookeeper or something. It's kind of the guts of the system. No, exactly. It's weird. We'll talk about it one day. Just it would take a whole hour to go through it. And yeah.
Okay, so great presentation, by the way. Thanks.
Thank you.
Thanks for having us here. One question regarding the architecture. It seems like a lot of systems are built around object store nowadays. You guys and then Neon also come into, GA recently. What happened recently, like maybe in 2018 onwards? What happened at that time? What that led to this kind of lot of systems coming into picture suddenly, actually?
I think it's just taken time for people to figure out how to do it. Also, object storage has just gotten better. Like trying to do this 10 years ago, the kind of P99 outlier latencies you would see would be crazy. But most object store implementations these days are pretty good. That's part of it. Like, for example, people have been building data lakes and data warehouses on top of object storage for like 10 years. Like, I don't know when Snowflake was founded, but I think it was like 8 or 10 years ago, right? No one you probably don't know anyone who uses Vertica anymore, right? Like you might know a couple of people who use like HDFS, but like most people's data lakes run on top of object storage. We've been doing that for a long time. People know how to do that. I think building a streaming system on top of an object store is kind of a harder building a data lake on top of an object store. Latency is much more important. The semantics are weirder, ordering matters. But yeah, like you said, people are starting to figure it out, and once someone does it, then people realize it's possible, and a lot of people start doing it.
Will there be a Jepsen report in the foreseeable future?
No, we use a product called Antithesis instead. And it gives you, it's like a Jepsen test on steroids. It's much more rigorous than Jepsen. You can go, there's a blog post about it on our website, but basically the company Antithesis has built a hypervisor that is completely deterministic, and does a bunch of really intelligent stuff to kind of like fuzz your software. And you can run multiple Docker containers. So every night we ship a new build to Antithesis, and they run essentially tests against WarpStream basically all night. And they inject faults, they introduce thread sleeps, they introduce network partitions, and our tests basically ensure that all of the semantics of Kafka are upheld during that time. So I think Jepsen tests are dead, personally. I think now that Antithesis exists, there's no reason to do a Jepsen test. Yeah.
I know you support MinIO as well. Do you have any latency numbers on MinIO?
Yeah, it works on Minio, R2, Oracle Cloud, anything that looks, we need put, list, get, and delete. That's basically it. So
And are the latency numbers any different from S3?
Minio would probably be way lower latency than S3 if you're running your own Minio cluster on SSDs. That's almost certain. I don't remember how R2 holds up in terms of latency, and I haven't done much benchmarking on Oracle Cloud. But Minio is, I mean, Minio, like you control the disks, right? So if you ran Minio on your node, on your own EC2s, you could make it really fast. But it's expensive to do that if you want Minio to be in multiple AZs. So
Thank you.
Thank you, Richard. We'll take rest of the questions if there are any offline. We'll have a break right after the next talk. But thank you so much, Richard, for a wonderful presentation.
Thank you.
For you.
Yeah, thank you for having me.